What would you do if the moon suddenly felt smaller and stranger than you remembered? Tonight we start with a simple puzzle. The moon seems familiar, yet it hides secrets that surprise scientists and storytellers alike. Over the next 47 minutes, we will reveal 33 mysterious facts that make our nearest neighbor far more curious than its calm face suggests. Stay with me, because each fact peels back a layer of a story that's been unfolding for billions of years. You might wonder why 33 facts and not 10 or 100, and there is a reason for that choice. 33 gives us room for big scientific revelations, weird anomalies, and human stories without getting lost in trivia. Each fact here is surprising, evidence-based, and often tied to an open question scientists still wrestle with. By the end, you'll have a textured view of the moon, part myth and part measurable science. The leading idea for the moon's birth is the giant impact hypothesis, which imagines Earth struck by a Mars-sized body over 4 billion years ago. That violent collision threw huge amounts of debris into orbit, and that material later coalesced to form the moon. This explains the moon's composition and angular momentum better than older ideas, although many details remain controversial and actively researched. Thinking of the moon as a scar-born child of Earth changes how we imagine planetary formation. One of the moon's simplest mysteries is the striking difference between the near side and the far side. The near side shows dark basaltic plains called maria, while the far side is heavily cratered and mountainous with far fewer maria. This asymmetry likely traces back to differences in crust thickness and volcanic history, but it still raises questions about early internal processes and impacts. The far side's ruggedness gives it a sense of unfamiliar territory, which puzzled early observers and still fascinates scientists. Those dark patches on the moon, called maria, are actually ancient basaltic lava plains formed by volcanic eruptions long ago. They filled huge impact basins, smoothing the surface and creating the distinctive darker areas we see from Earth. Most of the maria are between 3 and 4 billion years old, telling us about the moon's volcanic past and internal heat. The maria's locations and compositions help researchers reconstruct the moon's thermal evolution and internal structure. The moon isn't perfectly still. It experiences moonquakes that can be surprisingly strong. Some tremors come from tidal stresses caused by Earth's gravity, while others are triggered by meteorite impacts or thermal expansion of the surface at sunrise. Apollo seismometers recorded quakes that sometimes lasted for minutes because the moon's structure damps vibrations differently than Earth. Understanding these quakes matters for future habitats because they dictate how we design foundations and protect equipment on the lunar surface. Contrary to older ideas of a dry moon, scientists have detected water ice in permanently shadowed polar craters and trace amounts in the regolith. These cold traps preserve water molecules delivered by comets, asteroids, and perhaps solar wind interactions over eons. Finding water is a game changer because it can support future astronauts, serve as rocket fuel feedstock, and tell us about volatile delivery across the solar system. The distribution and accessibility of this water remain active research priorities. The moon lacks a thick atmosphere, but it does have a tenuous exosphere made of individual atoms and molecules. This exosphere is so thin that particles rarely collide, yet it contains elements like sodium, potassium, and traces of helium and argon. The exosphere changes over time as the solar wind, micrometeorites, and human activity interact with the surface. Even this whisper of atmosphere affects dust movement and the surface chemistry that scientists study from orbit and on-site. Lunar dust is notoriously abrasive and clings to everything, creating practical headaches for equipment and astronauts. Unlike earthly dust, Lunar regolith grains are sharp and irregular because they haven't been eroded by wind or water. Electrostatic charging from sunlight and the solar wind can make dust levitate and stick to surfaces, fouling seals and filters. Managing lunar dust is a major engineering challenge for long-term human presence, and it's why lunar suits and habitats need special dust control systems. The Moon is moving away from Earth at about 3.8 centimeters per year due to tidal interactions. As Earth's rotation transfers angular momentum to the Moon, tidal friction causes the Moon's orbit to slowly expand. This gradual drift affects Earth-Moon dynamics over geological timescales and has implications for ancient day length and tidal environments. Though the change is minute in human terms, it's measurable with laser ranging experiments and tells a deeper story about planetary evolution. The Moon keeps the same face toward Earth because it's tidally locked, meaning its rotation period matches its orbital period. This synchronous rotation developed over millions of years as tidal forces dissipated rotational energy, leading to a stable orientation. The result creates our familiar near side and an ever-hidden far side, which only spacecraft could reveal. Tidal locking is common in moons across the solar system and teaches us about long-term gravitational interactions. When the Soviet Luna 3 spacecraft first photographed the far side in 1959, scientists were astonished by how different it looked. The far side lacked the dark maria common on the near side and displayed more craters and rugged highlands. That revelation forced researchers to rethink early theories about lunar geology and interior dynamics. Those early images opened a new era of lunar exploration and curiosity about why the two hemispheres diverge so dramatically. Under some lunar basins lie dense regions called Mascons, short for mass concentrations, which perturb spacecraft orbits unpredictably. These high-density zones result from dense basalt filling impact basins or underlying structure variations, and they can pull orbiters closer if not accounted for. Mascons pose challenges for early missions and remain important for navigation and long-term satellite stability. Mapping them helps planners design safe lunar orbits and reveals clues about the Moon's internal structure. The South Pole-Aitken Basin is one of the largest and oldest impact structures in the solar system, spanning more than 2,000 kilometers. Its size hints at the colossal energies involved and provides a unique window into the Moon's deep crust or even mantle materials. Studying samples from this basin could reveal early differentiation processes and the Moon's composition at depth. That's why its exploration is a high priority for future missions and scientific inquiry. For a long time, scientists debated whether the Moon had a molten core at all, but seismic and magnetic data suggest a small, partially molten core exists. It's much smaller relative to its size than Earth's core, but its presence informs models of thermal evolution and ancient dynamo activity. The core's composition and size also affect how the Moon responded to impacts and tidal heating in its early history. Each piece of evidence refines our picture of lunar interior processes over billions of years. Even though the Moon lacks a global magnetic field today, parts of its crust retain strong remnant magnetism from an ancient time when a magnetic dynamo may have existed. These localized magnetic anomalies puzzle scientists because they suggest the Moon had magnetic activity earlier than previously thought. Studying those magnetic rocks helps reconstruct the Moon's thermal and rotational history. The patterns of magnetism may tie to impact events, volcanic activity, or an early core dynamo that later shut down. Observers have reported fleeting glows, flashes, and color changes on the Moon for centuries, collectively called transient lunar phenomena. While some events are likely caused by outgassing, impacts, or electrostatic dust activity. Others remain unexplained and controversial. Modern monitoring and satellite data help validate some sightings, but many reports remain anecdotal and puzzling. These ephemeral events remind us that the Moon is still an active place on human timescales in ways we are just beginning to measure. The Moon formed more than 4 billion years ago, and many of its surface features are preserved from that ancient era. Unlike Earth, which recycles crust through plate tectonics and erosion, the Moon's surface keeps a record of bombardment and volcanism. That preserved record is why lunar geology is central to understanding the early solar system. Every crater and basalt flow is a page in a history book far older than human civilization. Each lunar crater records a violent impact, and by studying their sizes, shapes, and distributions, scientists piece together the Moon's bombardment history. Larger craters often show central peaks and terraced walls resulting from rebound and collapse after the impact. Ejecta blankets and secondary craters reveal impact angles and energies, offering clues about solar system dynamics. In effect, the lunar surface is a forensic scene that helps reconstruct billions of years of cosmic collisions. Because the Moon lacks wind and rain, footprints and other human marks can remain for millions of years unless disturbed by impacts or micrometeorites. That preservation gives Apollo artifacts an almost archaeological permanence, creating a time capsule of early human exploration. However, tiny dust movements and occasional impacts will slowly degrade surfaces over geological time. The idea of leaving a mark that could outlast humanity is part of the emotional power of lunar exploration. The Moon's apparent brightness changes not just with phase, but because different regions reflect sunlight differently. Earthshine, sunlight reflected from Earth back to the Moon, can softly illuminate the dark portion of a crescent moon, creating a ghostly glow. The Moon's average reflectivity, or albedo, is low compared to Earth because its surface is covered with dark basalt and dusty regolith. These variations in reflectivity affect how we remotely measure surface minerals and textures. The Moon's gravity creates the familiar tides on Earth by pulling ocean water toward it and creating a bulge on the opposite side. These tidal forces influence coastal ecosystems, marine life, and even the long-term evolution of Earth's rotation. Tides also helped shape early life, providing intertidal environments where chemistry and biology could interact. The Moon's subtle gravitational hand has steered geological and biological processes on Earth in ways we're still unraveling. Although the Moon is tidally locked, a gentle wobble called libration lets us see about 60% of its surface over time. This rocking motion comes from the Moon's elliptical orbit and tilt, revealing regions near the edges that otherwise hide. Libration provided extra material for telescopic mapping and helped early astronomers catalog more of the lunar surface. It also offers richer sampling opportunities for missions, since more terrain becomes observable and targetable. The lunar rock and soil samples returned by Apollo missions revolutionized planetary science by providing ground truth for remote observations. These samples show the Moon's ancient ages, volcanic history, and impact record, and they serve as benchmarks for studying other worlds. They also revealed surprising chemical differences from Earth, prompting fresh questions about formation and evolution. Preserving and reanalyzing these samples with modern techniques continues to yield new discoveries decades after they were collected. The Moon helps stabilize Earth's axial tilt, which moderates seasonal extremes and contributes to a relatively steady climate over long timescales. Without the Moon, simulations suggest Earth could experience chaotic tilt variations that dramatically change climate patterns and possibly affect life's evolution. This stabilizing role is subtle but important, offering one explanation for why Earth developed such a hospitable long-term climate. It's remarkable to think our large moon plays a protective, planetary role for life here. During a total lunar eclipse, sunlight passing through Earth's atmosphere refracts and filters, casting a reddish glow on the moon. The color and intensity of that glow can reveal details about Earth's atmospheric composition and particulate content. Volcanic eruptions, for example, can darken eclipses by injecting aerosols into the stratosphere. Astronomers use these subtle cues to study both our atmosphere and the interplay of light and planetary shadows. The moon's reflectivity varies because of differences in surface materials, and interpreting that reflectivity requires careful spectroscopy. Dark maria contain iron-rich basalt that reflects less light, whereas the bright highlands are composed of anorthosite that reflects more. Remote sensing across different wavelengths helps identify minerals and glassy impact materials, but surface dust complicates interpretations. Combining albedo data with sample analysis gives the clearest picture of how the moon's surface formed and changed. The constant stream of charged particles from the sun, called the solar wind, continuously modifies the moon's surface by implanting hydrogen and helium and sputtering atoms into space. These processes create a thin veneer of altered material that scientists can analyze to learn about solar history. Solar wind interactions also contribute to the production of water molecules and other volatiles on the lunar surface. Understanding this interplay helps decode both lunar chemistry and the sun's long-term behavior. Because the moon's surface preserves impact craters, scientists use crater counts as a clock to estimate surface ages across different regions. By comparing crater densities and sizes, researchers infer when major bombardment events occurred and how volcanic resurfacing erased older records. This crater record helps calibrate models not just for the moon, but for other rocky bodies in the solar system. It's a kind of cosmic stratigraphy that ties local geology to solar system-wide events. As the lunar surface moves from night to day, severe temperature swings cause rocks and regolith to expand and contract, producing tiny thermal moonquakes. These stresses can create microfractures and loosen surface material, contributing to the slow evolution of the regolith. Thermal effects are most dramatic near terminators where sunlight sharply changes, and they play a role in how dust moves and how instruments age. Accounting for thermal stress is critical when planning surface operations and long-duration equipment. While the moon looks monochrome to the naked eye, multispectral imaging reveals subtle color variations tied to composition. False color images bring out differences in titanium, iron, and glassy material, helping scientists map basaltic provinces and volcanic deposits. These spectral colors become essential when choosing landing sites or sampling strategies, because they indicate unique geologic processes. What seems gray and uniform from Earth hides a colorful chemical tapestry under scientific scrutiny. Subsurface ice hidden in polar cold traps offers more than just water for future explorers. It holds a record of volatile delivery and solar system chemistry. These deposits can be layered and mixed with regolith, preserving signatures of cometary impacts and ancient solar wind interactions. Radar and neutron spectroscopy are tools used to detect and map these ice deposits, although interpreting the data requires careful modeling. The presence and depth of subsurface ice influence both science goals and resource strategies for lunar missions. The lunar South Pole is a hot target for exploration because it combines permanently shadowed cold traps with sunlit peaks that get near-continuous sunlight. That combination could provide water ice in the shadows and steady solar power on elevated terrain, making it ideal for long-term bases. The complex illumination and rugged terrain pose landing challenges, but the scientific and resource payoff explains the focus on this region. Future missions aim to map it in fine detail to identify safe landing sites and ice-rich deposits. The Moon orbits Earth in an ellipse, not a perfect circle, which creates varying distances that affect tidal strength and apparent size from Earth. When the Moon is at perigee, it appears slightly larger and leads to higher tides known as perigean spring tides. These variations influence eclipse geometry as well, sometimes creating total eclipses and other times annular ones. Orbital eccentricity and inclination are small but have measurable effects on the Earth-Moon relationship. Evidence from lunar samples and magnetometers suggests the Moon once hosted a magnetic dynamo early in its history, creating a transient global field. The existence and longevity of that dynamo remain debated, but it would have influenced how the surface trapped and retained magnetic signatures. A stronger field could have shielded the early surface from solar particles and affected volatile behavior. Studying remnant magnetism helps reconstruct the Moon's thermal and rotational past and the timing of key events. By now you might notice a theme. The Moon gives clear clues but often raises more questions than answers. Its preserved ancient surfaces are a double-edged sword, offering insights yet demanding careful interpretation. New technologies and missions keep revealing surprises, so lunar science is part history lesson and part ongoing detective story. This tension between knowledge and mystery is what keeps researchers and explorers coming back to study our nearest neighbor. One concrete challenge for returning humans is the relentless problem of lunar dust that abrades seals and electronics. Apollo astronauts reported suit wear and contamination, and future habitats will have to manage this sticky, sharp particulate. Engineers need to design airlocks, filtration systems, and resilient materials that cope with dust over months or years. Solving this practical problem is as crucial as rock sampling if humans are to live and work on the Moon sustainably. Without Earth's protective magnetic field and thick atmosphere, the lunar surface is exposed to cosmic rays and solar particle events that pose real risk to humans and electronics. Shielding strategies include regolith berms, underground habitats, and advanced materials to reduce dose rates. Predicting and reacting to solar storms will be essential for safe operations, especially during long stays. Addressing space weather challenges requires a mix of forecasting, engineering, and operational planning. Temperatures on the Moon swing from blistering heat to bitter cold because there's no atmosphere to buffer changes, challenging power systems and habitat thermal control. Equipment must handle high daytime temperatures near 120 degrees Celsius and plummet to minus 170 degrees Celsius at night in many places. Thermal cycles also stress materials and electronics and complicate human comfort and operations. Engineers are developing systems that store heat, insulate habitats, and operate reliably across these extremes. Before humans return in force, robotic scouts will map hazards, locate resources, and test technologies in situ to lower mission risk. These machines can carry drills, spectrometers, and ground-penetrating radar that identify ice, volatile layers, and suitable base locations. They also test communication relays and autonomous navigation across rugged, shadowed terrain. Combining robotic groundwork with human adaptability is a practical pathway to sustainable lunar presence and long-term science returns. Modern lunar exploration increasingly emphasizes international partnerships and commercial participation to spread costs and expertise. Different nations bring unique technologies, scientific priorities, and logistical contributions that enrich missions and increase redundancy. Collaborative frameworks also raise legal and governance questions about resource use and coordination. In practical terms, international cooperation accelerates science, spreads risk, and fosters a shared vision for the lunar future while requiring careful diplomacy and norms. Resource extraction on the Moon, especially water ice for fuel and life support, is a major driving force behind future missions and has commercial potential. Mining involves excavation, heating, and chemical processing to separate water from regolith, a set of technologies still in development. Success would reduce the need to launch everything from Earth and enable deeper space exploration using in-space refueling. However, mining raises technical, environmental, and legal questions about how to manage and share resources ethically. The Moon's far side offers a radio-quiet environment ideal for low-frequency astronomy shielded from terrestrial interference. Arrays placed there could study the early universe's dark ages and faint planetary signals that Earth-based telescopes cannot detect. Building and operating instruments on the far side is difficult because direct radio contact with Earth is blocked, requiring relay satellites. If achieved, far-side observatories could open new windows into cosmology and exoplanetary environments. Apollo landing sites are historic and scientific treasures that many argue should be preserved as heritage sites on another world. Protecting them from contamination or accidental damage will be a practical and ethical challenge as more missions visit. Preservation involves legal frameworks, technological markers, and mission planning that respects both scientific sampling and cultural significance. How we treat these sites sets precedents for future exploration and international norms in space. One promising shelter idea is to bury habitats under regolith to use the lunar soil as natural radiation shielding and thermal insulation. This approach leverages local material to reduce launch mass and provides robust protection against micrometeorites. Excavation techniques and 3D printed structures are under study to implement such designs. Living under regolith poses engineering and psychological challenges, but it offers a practical route to safe, long-term lunar habitation. In situ resource utilization, or ISRU, means producing air, water, fuel, and building materials from lunar resources rather than hauling them from Earth. Techniques include extracting oxygen from regolith, producing hydrogen from ice, and sintering soil into construction bricks. ISRU could transform mission economics and enable larger bases, but it requires scalable, reliable processes that operate in the lunar environment. Demonstrations in the coming decade will determine whether ISRU is practical at relevant scales for human missions. Because many promising scientific sites are in rugged or shadowed terrain, autonomous systems will be essential to explore where humans can't safely go. Drones, tethers, and adaptable rovers can map caves, steep slopes, and permanently shadowed rims to identify ice deposits and geological exposures. Autonomous exploration reduces risk and expands the range of accessible discoveries, but it demands robust AI, reliable autonomy, and fault-tolerant systems. These technologies will pair with human crews to maximize scientific returns. A commercial lunar economy could emerge around transportation, resource extraction, research, and even tourism, but it will require legal frameworks and significant investment. Private companies are already developing landers, rovers, and prospecting tools that promise to open new markets. The interplay between national programs and commercial interests will shape priorities and standards for access, sustainability, and benefit sharing. If managed responsibly, commercial activity could accelerate exploration and scientific knowledge while posing governance challenges. Certain scientific tasks still benefit enormously from human judgment and dexterity, such as selecting unusual samples, performing complex field experiments, or adapting to unexpected discoveries. Apollo demonstrated how much faster humans can collect diverse, high-quality samples compared to robots alone. Combining humans' flexibility with robotic persistence offers the best path to deep scientific returns, especially for geology, complex instrumentation, and on-the-spot hypothesis testing. Future missions aim to leverage both strengths strategically. As activity on the Moon increases, legal and ethical questions about resource rights, environmental protection, and heritage preservation become urgent. International treaties like the Outer Space Treaty set broad principles, but they leave many operational details unresolved for mining and commercial uses. Creating fair, practical frameworks for access, responsibility, and conflict resolution is essential to prevent disputes and ensure sustainable exploration. This governance challenge is as important as engineering and science for the Moon's future. Communicating with assets on the Moon's far side requires relay satellites because the Moon blocks direct radio contact with Earth. Building and maintaining a robust relay network adds cost and complexity, but enables science operations and eventual far-side bases. Satellite placement in lunar orbit or at Earth-Moon Lagrange points provides options, each with trade-offs in coverage and fuel requirements. Reliable communication architecture is a backbone requirement for any sustained far-side exploration. Permanently shadowed regions host valuable ice but lack sunlight, presenting a power dilemma for mining and exploration. Possible solutions include placing solar arrays on nearby sunlit peaks and beaming power, using radioisotope or small nuclear reactors, or building long-run battery systems. Each option carries engineering and political considerations, but a reliable power supply is essential for continuous operations in these dark, cold regions. Solving the power puzzle unlocks the most promising science and resource opportunities. Putting humans back on the Moon means integrating life support, radiation protection, dust control, and contingency planning into a unified mission architecture. Training, medical protocols, and redundancy in systems are critical to handle emergencies far from Earth. The Artemis program and international partners are working through these operational challenges to ensure safe returns and sustainable presence. Each detail must be tested rigorously, because the Moon offers little margin for error when human lives are at stake. The scientific payoffs from a sustained lunar program extend across geology, heliophysics, astronomy, and perhaps even biology if we test life support systems. Instruments placed on and beneath the surface can reveal ancient records of solar system evolution, solar activity, and planetary formation. Each new dataset refines our models and points to new questions, creating a virtuous cycle of discovery. Ultimately, the Moon acts as both a laboratory and a stepping stone for broader exploration of the solar system. The discovery of usable water ice on the Moon is the narrative hinge between science and a new era of exploration, enabling fuel production, life support, and sustainable presence. Turning ice into hydrogen and oxygen could allow lunar refueling depots that make missions to Mars and beyond more feasible. This technical pivot transforms the Moon from a destination into a logistics hub and forces us to consider long-term stewardship. The challenge now is to scale these processes responsibly and ethically. The Moon teaches us about cosmic violence, geological time, and how a single celestial neighbor can shape an entire planet's destiny. From ancient myths to modern rockets, our view of the Moon mirrors advances in science, technology, and culture. Each mission and discovery adds a line to an ongoing conversation between humanity and its nearest celestial companion. Listening to that conversation helps us plan better science, fairer governance, and wiser exploration. We've woven 33 threads together into a tapestry that shows the moon as ancient, active, resource-rich, and scientifically invaluable. From impact origins and volcanic maria to ice, mascons, and future bases, each fact changes how we think about our lunar neighbor. The moon is both a laboratory for fundamental science and a proving ground for human expansion into the solar system. As we look ahead, these 33 mysteries offer priorities and inspiration for the next generation of explorers. When you see Earthrise from the moon, planetary boundaries blur, and the fragility of our home becomes obvious and precious. The moon's mysteries remind us how much we can still learn when we combine curiosity with care. Exploring responsibly means preserving scientific value while building capabilities for broader discovery, and it requires international cooperation and ethical frameworks. If we succeed, the moon will remain a source of wonder and a stepping stone to the stars. Humanity stands at a crossroads where scientific curiosity, commercial opportunity, and international cooperation could converge to open a sustained presence on the moon. The technical and ethical challenges are real, but so are the potential benefits for science, exploration, and inspiration. As we step forward, remembering the moon's 33 surprises helps us set wise priorities and respectful practices. Subscribe for more,